Hi there, welcome back to this video on lesson 5. We're talking about inequalities for polynomial and rational functions. This video will specifically cover inequalities for rational functions. Remember, in video 1, we talked about how to solve an inequality, right, which is a mathematical statement involving an inequality symbol. Where we went ahead and identified zeros, we put numbers on a number line, and then we tested. And you can see this here, this example for polynomials. So we picked numbers on intervals between the zeros, and we tested. Or we could graph. Now with polynomial functions, we are going to specifically test. So here is a rational function, and our sign can change at a couple of things. They can change at zeros. They could change at zeros. They can change at inequalities. They can also change at wholes if you have a whole at a 0. So we have to go ahead and we have to determine wholes, vertical asymptotes, and real zeros, and then we will place these values on a number line. Mark the zeros with a closed dot, undefined values with an open dot, and then I like to give a dashed line for an asymptote. And then again, we'll choose numbers and we will test and then write the solution using the inequality symbol, okay? So let's go ahead and jump into example number 1. Here they say the rational function r is given by r of x, where r is equal to x squared minus 4 over x squared plus 3x minus 10. On what intervals of x is r of x greater than or equal to 0? So the first thing I'm going to do is I'm going to factor this expression, x minus 2, x plus 2, divided by x plus 5, x minus 2. And what I notice about this expression is that we have a whole at 2. And when I reduce, I get x plus 2, and we get x plus 5, okay? So what I notice about this is we have a whole at x equals 2. I notice that we're going to have a 0. When I set this equal to 0, I just get x plus 2. We're going to have a 0 at x equals negative 2. And our asymptote, the factor in our denominator, we're going to have a vertical asymptote at x equals negative 5. So all of these numbers will make it onto our number line. Negative infinity, positive infinity, and I'm going to go ahead, what do we got? Negative 5. Okay, here's negative 5. And then we have a 0. So I'll put a closed dot at negative 2. And then we have a whole at 2. This is at 2, okay? So just kind of talking about what we can expect from a rational function. You can expect signs to change at a vertical asymptote. Especially if it's an odd vertical asymptote. If it's even, it won't change. They'll both come from the same direction. But again, make sure you test. So unless you have specific knowledge about the structure of a rational function, you won't know automatically if they change, okay? So degree 1, they are going to change. I can expect a sign change. They will change at a 0. We can expect when we cross the 0, right? Unless I have multiplicity, which I don't. And then at a whole, it's unlikely, unless that whole was also a 0, unless that factor survived in the numerator, likely that won't cross, okay? But we're going to go ahead and we're going to test, right? So this is step 1. Find these key features. Step 2, place them on a number line. Step 3, we're going to go ahead and test. So I'll check negative 10, and I get r of negative 10. And again, I'm just going to use the reduced function. I'm going to plug it in, and all I care about is the sign. So negative 10 plus 2, that's negative, divided by negative 10 plus 5 is again a negative. So a negative over a negative, positive. We're positive on this interval, okay? And then I'm going to choose negative 4. We'll choose negative 4. R, negative 4. Okay, and we get a negative over a positive. So we get a negative, just like we suspected. We'll change signs at the asymptote, right? One side's going to go up, one side's going to go down. And then choose 0. Always choose 0. If you can choose 0, 0 is the best. We get 2 over 5. That's positive over a positive. So this is, this interval is positive at 0, which again we expected, right? Crossing. And then I'm going to choose 10. This is unlikely to change here because it wasn't a 0, and we get a positive over a positive, right? 10 plus 2, 10 plus 5, that's going to be a positive value, okay? All right, so what do they want? They want to know where is r of x greater than or equal to 0. If it's equal, guess what? We are including -2 in our domain. We are including -2. So where are we greater than or equal to? Well, on this interval, looks like this interval right here, from -infinity to -5. So I'll say x is less than -5. That's first interval. Second interval, it looks like it's going to be from -2 to 2. From -2 to 2. But again, I'm including the -2 because it's a 0. I leave out 2 because it's a whole. And then we go from values bigger than 2. So that's x is greater than 2. I don't include the 2 because it's not, it's a domain restriction. Okay. So, this is inequality. Here they use interval notation, but that's going to be A. Answer here is A. All right, let's go ahead and look at example number 2. Rational function g is given by g of x equals 4x minus 12 divided by 3x. On what intervals of x is g of x less than or equal to 0? So this one, I guess you do have a factorization. You could do a GCF. I'm not going to do that. I'm just going to go ahead and find my 0. So 4x is equal to 12, so x is equal to 3. And then what I also notice is that we have a vertical asymptote at x equals 0. So on this number line, I have a 0, right? This is a 0. I just set my numerator equal to 0. So we have 3. And then I have a vertical asymptote at 0. Both of these are likely to cause change, okay? So let's test. I'm going to test -1, I'll test 1, and then we'll test 10. So g of -1 is going to give me a negative divided by a negative, which is positive. Okay, right? -1 plugged in, -4 minus 12, -3. And then 1 is likely to give me a negative over a positive, a negative number over a positive number, right? When I plug in 1, 4 times 1, 4 minus 12 is negative. This is negative. So again, like we thought. And then let's plug in 10. If I plug in 10, 4 times 10, ooh, that's much bigger than that -12. So that's a positive quantity. And 3 times a positive 10 gives us a positive. So this is positive. Okay, where are we less than or equal to 0? Well, that's going to be this interval, 0 to 3. But again, it's equal to. Do you see how it's equal to 0? We were going to include that 3. So 0 to 3 is what we want. Looks like B is our answer, B. Okay? All right. Practice problem. Please go ahead, pause the video, try this one, and I will pop up the solution and then talk through it. Okay, here is my solution work. I factored h, and I noticed we had a shared factor at x plus 5, so that's going to give you a whole at -5. After we reduce, we get x over x minus 5. The 0 is in the numerator. That's going to give you a 0 at 0. And the denominator causes a vertical asymptote at x equals 5. We place these key features on the number line, and here I color-coded them to match, right? Here's the whole, here's the 0, here's the asymptote, and then I chose values to test. So again, I like the 10s, I like the 1s, and then 0 here was in use, so I couldn't test 0. But this is the results that I got. So you can double check, see if it matches you. It looks like we're positive here, negative here, and positive. They want to know where is our function greater than or equal to 0. So this is positive and equal to 0. So we'll include the 0. So where does this happen? Well, that's going to happen for all of these values right here, right? So where x is less than -5. And then for this interval here, we go from -5 all the way to 0. We, again, include the 0. And then it looks like for this one, x is greater than +5. So what is that going to give us? B. I like B. Did you get B? Hopefully you got B. B is the answer. Okay, in this video we went ahead and we talked about how to solve rational inequalities. Find the zeros, find the holes in asymptotes, put it on a number line, plot and test. Very similar to a polynomial inequality. If you learned something, give this video a thumbs up. I'll catch you in the next math video. See ya.